Welcome to the subconscious library. Tonight, we're leaving Earth behind. For the next hour, there is nowhere you need to be, nothing you need to remember, and certainly no test at the end. You can simply listen. We'll travel outward from our small planet, past the moon, beyond the planets, through stars and nebulae, across enormous galaxies, and eventually toward the furthest reaches of the universe we can observe. Some of what you hear may be familiar. Some of it may be strange. And some of it may make Earth feel very, very small. So get comfortable. Close your eyes if you'd like. And let's begin with the only place in the universe that every human being has ever called home. Earth is about 4.54 billion years old. That sounds unimaginably ancient, but the universe itself is roughly 3 times older. If the entire history of Earth were compressed into a single 24-hour day, human civilization would appear only in the final fraction of a second. For almost all of our planet's existence, there were no cities, no roads, no books, and no humans looking toward the stars. Earth is the largest of the 4 rocky planets in our solar system. But compared with the larger planets beyond Mars, Earth is quite small. Jupiter is so large that more than 1,000 Earths could fit inside it by volume. Yet Earth has something we have not yet confirmed anywhere else. Life. We know that life appeared on Earth at least billions of years ago. Exactly how the first living systems formed remains one of science's great unanswered questions. Our planet happens to orbit within a region around the Sun, where temperatures allow liquid water to exist on the surface. Astronomers sometimes call this the habitable zone. But being inside a habitable zone does not automatically make a planet habitable. A planet also needs the right atmosphere, chemistry, geological history, and many other conditions. Earth's atmosphere is mostly nitrogen. About 21% is oxygen. The oxygen we breathe did not always exist in such abundance. Much of it accumulated because ancient microorganisms released oxygen through photosynthesis. In a very real sense, the atmosphere around you was shaped by life long before animals existed. Earth is also constantly moving. Even while you lie completely still, the planet is rotating. Near the equator, the surface moves at more than 1,600 kilometers per hour because of Earth's rotation. At the same time, Earth travels around the Sun at roughly 30 kilometers every second. And the Sun itself is moving through the Milky Way. There is no absolute cosmic sense in which you are sitting still. You are always traveling. Earth's rotation gives us day and night. Its 23.5-degree axial tilt gives us the seasons. A common misconception is that summer happens because Earth is closer to the Sun. But Earth's distance from the Sun changes only modestly over the year. Instead, summer occurs when your hemisphere is tilted toward the Sun, causing sunlight to arrive more directly and for longer portions of the day. Earth is not a perfect sphere. Its rotation makes it bulge slightly around the equator. The distance from Earth's center to the equator is a little greater than the distance from the center to the poles. Our planet also has a powerful magnetic field. Deep beneath our feet, moving liquid metal in Earth's outer core helps generate this enormous magnetic environment. It stretches far into space and helps deflect many charged particles arriving from the Sun. When some of those particles interact with Earth's upper atmosphere near the poles, they can produce auroras. The northern lights and southern lights are therefore not simply atmospheric phenomena. They are visible evidence of an interaction between Earth and the Sun, happening hundreds of kilometers above the ground. Above that atmosphere is space. But there is no perfectly sharp boundary where Earth suddenly ends and space begins. The atmosphere simply becomes thinner and thinner. A commonly used boundary is the Kármán line, about 100 kilometers above sea level. From there, Earth looks very different. There are no visible national borders, no lines dividing countries, only oceans, continents, clouds, and the thin atmosphere surrounding the planet. That atmosphere looks substantial from the ground. From orbit, it appears astonishingly fragile. And circling Earth is our nearest celestial neighbor. The Moon is approximately 1/4 of Earth's diameter. It is unusually large compared with its planet. Most moons in our solar system are much smaller relative to the worlds they orbit. Scientists believe the Moon probably formed very early in Earth's history, after a massive collision. According to the leading explanation, a young Earth was struck by another planetary body. Material blasted into orbit eventually gathered together and formed the Moon. The Moon is slowly moving away from Earth. Measurements using lasers reflected from mirrors left on the lunar surface show that its distance increases by roughly a few centimeters each year. Long ago, the Moon therefore appeared larger in Earth's sky, and Earth's days were shorter. The gravitational interaction between Earth and the Moon gradually slows Earth's rotation while transferring energy to the Moon's orbit. The Moon always shows us nearly the same face. This happens because its rotation period is synchronized with the time it takes to orbit Earth. It rotates once on its axis during each orbit around our planet. This phenomenon is called tidal locking. There is therefore a far side of the Moon, but not a permanently dark side. The far side receives sunlight just as the near side does. The Moon has essentially no thick atmosphere. Without a substantial atmosphere to distribute heat, temperatures vary enormously. Sunlit areas can become extremely hot. Nighttime regions can become brutally cold. And because there is almost no air, sound cannot travel across the lunar surface the way it does on Earth. If two astronauts stood apart on the Moon without radios, they could not simply shout to one another. The Moon's gravity is around 1/6 as strong as Earth's. A person who weighs 180 pounds on Earth would weigh about 30 pounds on the Moon, although their mass would remain unchanged. Footprints made on the Moon can remain for extraordinarily long periods because there is no ordinary wind or rain to erase them. Eventually, tiny meteorite impacts and other processes will disturb them. But compared with footprints on Earth, they are remarkably persistent. The Moon also affects Earth's oceans. Its gravity contributes heavily to the tides. And the Moon appears almost exactly the right size in our sky to cover the Sun during a total solar eclipse. This is a cosmic coincidence. The Sun is roughly 400 times wider than the Moon, but it is also roughly 400 times farther away. So from Earth, they appear similar in angular size. Because the Moon is slowly moving away from us, this arrangement will not last forever. Far in the future, total solar eclipses, as we know them, will no longer occur. Now let us travel much farther. About 150 million kilometers from Earth lies the object responsible for nearly every sunrise our planet has ever experienced. The Sun is a star. It looks fundamentally different from the stars visible at night only because it is vastly closer. The nearest other star system is more than 4 light-years away. The Sun, by comparison, is only about 8 light-minutes from Earth. That means sunlight reaching your face began its journey from the Sun roughly 8 minutes earlier. If the Sun could somehow disappear instantly, we would not know immediately. Its final light would continue arriving for those 8 minutes. The Sun contains almost all the mass in the solar system. Planets, moons, asteroids, comets, and everything else make up only a small fraction of the total. About 1 million Earths could fit inside the Sun by volume. And yet among stars, the Sun is not particularly enormous. It is often informally described as an average-sized star, although stellar populations are complicated and many stars are actually smaller red dwarfs. The sun shines because of nuclear fusion occurring in its core. Their temperatures and pressures are so extreme that hydrogen nuclei ultimately combine to form helium. A small amount of mass is converted into energy. This process powers the sun. Every second, enormous quantities of hydrogen are fused. The energy produced deep inside the sun does not simply travel straight outward. Photons may undergo countless interactions before eventually reaching the surface. Energy generated in the core can take an extremely long time to work its way outward through the sun's interior. But once light leaves the visible surface, it needs only around 8 minutes to reach Earth. The sun's visible surface is called the photosphere. Its temperature is around 5,500 degrees Celsius. Above it lies the corona, an outer atmosphere that extends millions of kilometers into space. Strangely, the corona is far hotter than the visible surface below it. Understanding exactly how the corona is heated has been a major problem in solar physics. During a total solar eclipse, the bright disk of the sun is blocked by the moon, allowing the faint corona to become visible from Earth. The sun is not perfectly calm. Its magnetic field can become tangled and rearranged. This activity creates sunspots, solar flares, and enormous eruptions called coronal mass ejections. When material from these eruptions reaches Earth, it can disturb our planet's magnetic environment. Strong solar storms can affect satellites, radio communication, electrical systems, and navigation technology. They can also produce spectacular auroras. The sun has been shining for around 4.6 billion years. It will not shine in its present form forever. As it gradually exhausts hydrogen in its core, its internal structure will change. In roughly 5 billion years, the sun is expected to expand into a red giant. Its outer layers will grow enormously. Mercury and Venus will likely be engulfed. Earth's distant fate is more complicated, but our planet will become uninhabitable long before that stage. Eventually, the sun will shed its outer layers. Its remaining core will become a white dwarf, a dense stellar remnant roughly comparable in size to Earth, containing a significant fraction of the sun's current mass. It will slowly cool over immensely long timescales. But for now, the sun remains a stable star in the middle of its long life. And orbiting nearest to it is Mercury. Mercury is the smallest planet in our solar system. It is also the closest planet to the sun. Despite that, Mercury is not the hottest planet. That title belongs to Venus. Mercury has very little atmosphere to retain heat. During its daytime, temperatures can become extraordinarily high. During its night, temperatures plunge far below freezing. A day on Mercury is strange. Mercury rotates very slowly. It takes about 59 Earth days to rotate once relative to distant stars. But because the planet is simultaneously moving around the sun, the time from one sunrise to the next is about 176 Earth days. In other words, a solar day on Mercury lasts longer than its year. Mercury completes an orbit around the sun in only 88 Earth days. Its surface is heavily cratered. At first glance, photographs of Mercury can resemble our moon. But Mercury has a surprisingly large metallic core. Its interior has fascinated planetary scientists because the core occupies a very large portion of the planet. Despite its proximity to the sun, Mercury may contain water ice. Deep craters near its poles contain regions that remain permanently shadowed. Temperatures inside these areas can stay cold enough for ice to survive. So one of the closest worlds to the sun may still preserve frozen water in darkness. Moving outward, we encounter a planet sometimes called Earth's sister. But the resemblance is deceptive. Venus is one of the most hostile places in the solar system. Venus is almost the same size as Earth. Its mass and diameter are relatively similar to ours. From a distance, one might imagine the planets developing in similar ways. They did not. Venus has an extremely thick atmosphere dominated by carbon dioxide. Its surface pressure is around 90 times that at sea level on Earth. Standing there would mean experiencing pressure comparable to being deep beneath Earth's ocean. Its clouds contain sulfuric acid, and its surface temperature is hot enough to melt lead. Venus is hotter than Mercury, even though Mercury is closer to the Sun. The reason is Venus's powerful greenhouse effect. Heat becomes trapped by its thick carbon dioxide atmosphere. Surface temperatures remain around 460 degrees Celsius. Day or night, near the equator or elsewhere. The planet is essentially a global furnace. Venus also rotates in an unusual direction. Most planets rotate in the same general direction as they orbit the Sun. Venus rotates backward compared with most of them. If you could somehow stand safely on Venus's surface and see through its clouds, the Sun would appear to rise in the west and set in the east. Its rotation is incredibly slow. One rotation takes about 243 Earth days. That is longer than Venus takes to orbit the Sun. A Venusian year lasts only about 225 Earth days. The planet's surface contains enormous volcanic plains, mountains, and evidence of extensive geological activity. Scientists continue investigating whether some volcanoes may still be active today. Then we arrive back at Earth. And beyond Earth, the next planet is Mars. Mars has fascinated humans for centuries. It appears reddish because iron minerals in its soil have oxidized. Essentially, much of the surface contains rust. Mars is smaller than Earth. Its gravity is about 38% as strong. A 180-pound person would weigh only around 68 pounds there. Mars has a day remarkably similar in length to ours. A Martian day, often called a sol, lasts about 24 hours and 39 minutes. Its year, however, lasts roughly 687 Earth days. Mars has seasons because its rotational axis is tilted. But its atmosphere is extremely thin compared with Earth's. It is mostly carbon dioxide. The planet is cold, dry, and exposed to much more radiation than Earth's surface. Mars contains the largest volcano known in the solar system, Olympus Mons. It rises more than 20 kilometers above the surrounding terrain. Its enormous size was made possible partly because Mars lacks the same kind of active plate tectonics that continually moves Earth's crust over volcanic hotspots. A volcano on Mars could remain above a source of magma for a very long period. Mars also contains Valles Marineris, an immense canyon system stretching thousands of kilometers. It dwarfs Earth's Grand Canyon. Today Mars appears dry, but its surface contains strong evidence that liquid water once flowed there. Ancient river valleys, lake beds, and minerals formed in the presence of water show that early Mars was very different. Mars may once have had rivers and lakes beneath a thicker atmosphere. Whether life ever developed there remains unknown. No confirmed evidence of Martian life has been discovered. But Mars remains one of the most important places in the search for ancient extraterrestrial biology. Mars also has two tiny moons, Phobos and Deimos. They are irregularly shaped and much smaller than Earth's moon. Phobos orbits unusually close to Mars. It is gradually spiraling inward. Far in the future, it may break apart or crash into the planet. Leaving Mars behind, we enter the asteroid belt. Movies sometimes portray asteroid belts as crowded fields of rocks where spacecraft must constantly dodge collisions. Our asteroid belt is nothing like that. It contains enormous amounts of empty space. A spacecraft can pass through it without weaving dramatically between rocks. The belt lies mainly between Mars and Jupiter. It contains countless objects left over from the early solar system. The largest object there is Ceres. Ceres is classified as a dwarf planet. It is large enough for its gravity to pull it into a roughly spherical shape. Despite containing many asteroids, the entire asteroid belt does not contain anywhere near enough material to form a planet the size of Earth. If all the material were combined, its total mass would still be only a fraction of our moon's. Jupiter's powerful gravity influenced the region strongly during the solar system's formation, preventing material there from easily combining into a full-sized planet. Asteroids vary enormously. Some are solid rock. Others contain significant metal. Some are loosely bound collections of debris, sometimes described as rubble piles. And some contain water-bearing minerals and organic compounds. These ancient objects act like preserved pieces of the solar system's earliest history. Then, beyond the asteroid belt, everything becomes much larger. We encounter Jupiter. Jupiter is the largest planet in our solar system. It is so massive that it contains more than twice the mass of all the other planets combined. Yet Jupiter is not a solid world like Earth. It is a gas giant composed primarily of hydrogen and helium. There is no ordinary surface where you could simply stand. As you descended into Jupiter, the surrounding pressure would increase enormously. Hydrogen would behave in increasingly strange ways. Deep inside, scientists believe hydrogen may enter a metallic state capable of conducting electricity. Jupiter rotates astonishingly quickly. Despite being enormous, it completes a rotation in roughly 10 hours. This rapid spin causes the planet to bulge around its equator. Its atmosphere contains powerful jet streams and enormous storms. The most famous is the Great Red Spot. This gigantic storm has existed for centuries. Although its size changes over time, it remains larger than Earth in at least one dimension. Jupiter also possesses an enormously powerful magnetic field. Its radiation environment can be extremely dangerous to spacecraft. And Jupiter has many moons. 4 of the largest were famously observed by Galileo Galilei in 1610. Io, Europa, Ganymede, and Callisto. Their discovery helped transform humanity's understanding of the heavens. Not everything, it turned out, orbited Earth. Io is the most volcanically active world known in the solar system. Jupiter's enormous gravity, combined with gravitational interactions involving the other moons, flexes Io internally. That tidal heating powers extraordinary volcanic activity. Europa is very different. Its surface is covered in ice. Beneath that frozen exterior, strong evidence suggests there is a global ocean of liquid water. The amount of water in Europa's ocean may exceed the amount found in all of Earth's oceans combined. This makes Europa one of the most intriguing locations in the search for environments that could potentially support life. Ganymede is the largest moon in the solar system. It is even larger than the planet Mercury. Ganymede is also the only moon known to generate its own intrinsic magnetic field. Callisto is heavily cratered and ancient. Its surface preserves a record of impacts stretching far back into solar system history. Jupiter's immense gravitational influence has shaped the architecture of the solar system. It can deflect comets and asteroids. Sometimes this helps protect the inner planets. Sometimes gravitational interactions can instead send objects toward them. Jupiter is therefore not simply Earth's cosmic shield. Its role is more complicated. Beyond Jupiter lies one of the most recognizable objects in astronomy. Saturn is famous for its rings. Other giant planets have rings too. but Saturn's are by far the most prominent. The rings are made primarily from countless pieces of water ice mixed with rocky material and dust. Some particles are tiny, others are much larger. The entire ring system stretches hundreds of thousands of kilometers across. Yet many portions are astonishingly thin compared with their width. If you could build a scaled model of Saturn's rings several meters across, the ring sheet would be extraordinarily delicate. The rings contain gaps and intricate structures shaped partly by the gravity of Saturn's moons. Some small moons orbit inside or near the rings and help sculpt their edges. Saturn itself is the second largest planet in the solar system. Like Jupiter, it is composed mostly of hydrogen and helium. Its average density is lower than the density of water. People sometimes say Saturn would float in an enormous bathtub. That statement is conceptually true in terms of average density, though finding a bathtub large enough would present a few obvious engineering problems. Saturn also rotates rapidly. A day lasts only about 10.5 hours. Powerful winds sweep through its atmosphere. Near its North Pole is one of the strangest weather patterns in the solar system. A giant hexagon. This six-sided atmospheric structure has persisted for decades of observation and surrounds the North Pole. Saturn has a remarkable family of moons. Titan is the largest. It is bigger than Mercury and possesses a thick atmosphere. Titan's atmosphere is mostly nitrogen. Its surface pressure is greater than Earth's. But Titan is extremely cold. Water ice there behaves almost like rock. And instead of a water cycle, Titan has a cycle involving methane and ethane. There are clouds, rain, rivers, lakes, and seas. But many of them involve liquid hydrocarbons rather than liquid water. Titan is the only world besides Earth known to have stable bodies of liquid on its surface. Another Saturnian moon, Enceladus, is much smaller. Yet it may be even more intriguing. Enceladus has an icy surface and a subsurface ocean. Near its south pole, enormous plumes eject water vapor and icy particles into space. Spacecraft have flown through these plumes and detected interesting chemistry. Because material from the hidden ocean naturally escapes into space, scientists can investigate it without drilling through kilometers of ice. Beyond Saturn lies Uranus. Uranus is an ice giant. It appears pale blue-green because methane in its atmosphere absorbs portions of red light. One of the strangest things about Uranus is its rotation. The planet essentially spins on its side. Its axial tilt is about 98 degrees. Scientists think a gigantic collision early in Uranus's history may have contributed to this unusual orientation, although the details remain uncertain. Because of that extreme tilt, Uranus experiences extraordinary seasons. Each hemisphere can spend decades receiving continuous sunlight, followed by decades of darkness. Uranus takes 84 Earth years to orbit the Sun, so each season lasts roughly 21 Earth years. The planet also possesses rings, although they are much darker and less obvious than Saturn's. Its atmosphere is extremely cold. Some measured atmospheric temperatures are among the lowest associated with any planet in the solar system. Then comes Neptune, the most distant major planet. Neptune orbits about 30 times farther from the Sun than Earth does. Sunlight there is dramatically weaker. A Neptune year lasts almost 165 Earth years. Since Neptune was discovered in 1846, it completed its first full orbit after discovery only in 2011. Neptune is another ice giant. Its deep blue appearance in many famous images has sometimes been enhanced during image processing, but methane still contributes to its blue coloration. Despite being so far from the Sun, Neptune has some of the fastest winds observed in the solar system. Atmospheric winds can reach well over 1,000 kilometers per hour. Neptune has a large moon called Triton. Triton is unusual because it orbits Neptune in the opposite direction from the planet's rotation. This strongly suggests Triton did not form alongside Neptune. It was probably captured by the planet's gravity. Triton may once have been an object similar to those found farther away in the Kuiper Belt. Its surface is extremely cold. Voyager 2 observed geyser-like activity there, with material erupting from the surface. Far in the future, Triton's unusual orbit may bring it close enough to Neptune that tidal forces tear it apart. It could eventually form a spectacular ring system. And beyond Neptune lies a region filled with frozen worlds. The Kuiper Belt. Pluto was discovered in 1930. For most of the 20th century, schoolchildren learned that it was the ninth planet. In 2006, the International Astronomical Union formally classified Pluto as a dwarf planet. Pluto has not disappeared. It has not physically changed. We simply changed the category we use to describe it. A major reason was that astronomers discovered other significant objects in the outer solar system, including Eris. If Pluto remained a planet under a broad definition, scientists might have needed to classify several additional objects as planets as well. Pluto is surprisingly complex. When the New Horizons spacecraft flew past it in 2015, it revealed towering mountains of water ice, vast plains of frozen nitrogen, and signs of active geological processes. One of Pluto's most recognizable features is a large heart-shaped region. Part of this area is called Sputnik Planitia. Pluto also has a large moon named Charon. Charon is more than half Pluto's diameter. The pair is so unusual that the point around which they orbit lies outside Pluto itself. Smaller moons also orbit the system. Beyond Pluto are countless icy bodies belonging to the Kuiper Belt and related populations. And far beyond even that may lie the Oort cloud. The Oort cloud is a hypothesized enormous reservoir of icy objects surrounding the solar system at immense distances. Long-period comets may originate there. If it exists as expected, the Oort cloud extends a significant fraction of the distance toward neighboring stars. At this point, our familiar planetary neighborhood begins to fade. So now we leave the solar system entirely and travel toward the stars. Every star you see at night is another sun. Some are smaller than ours. Some are far larger. Some are hotter. Some are cooler. Their colors provide clues about their temperatures. Blue stars are generally hotter than red stars. This may feel backward because on Earth we often associate red with heat and blue with cold. But stellar physics works differently. A star's color depends partly on the spectrum of thermal radiation emitted from its surface. The most common stars in the Milky Way are red dwarfs. They are smaller and cooler than the sun. Because they consume their nuclear fuel slowly, red dwarfs can survive for extraordinarily long periods, potentially trillions of years. The universe is only around 13.8 billion years old, so no red dwarf has yet had enough time to naturally reach the end of such a lifespan. The smallest red dwarfs alive today could therefore continue shining long after the sun is gone. Massive stars live very different lives. They contain much more fuel, but they burn through it extraordinarily quickly. Some of the most massive stars survive only a few million years. That means the brightest, most powerful stars can have some of the shortest lives. Stars form inside enormous clouds of gas and dust. Gravity causes regions of these clouds to collapse. As material gathers, the center grows hotter and denser. Eventually, conditions can become extreme enough for nuclear fusion to begin. A star is born. For most of its life, A star exists in a relatively stable balance. Gravity tries to compress it inward. Energy generated by fusion produces outward pressure. These competing effects hold the star in equilibrium. But eventually, its usable nuclear fuel changes. What happens next depends heavily on the star's mass. A star like our Sun eventually expands into a red giant. More massive stars can produce heavier elements through successive stages of fusion. Eventually, some reach iron. Fusing iron does not provide the same energy benefit needed to support the star. The core can collapse catastrophically, and the star may explode. A supernova. A supernova can temporarily become enormously bright. For a short period, one exploding star may rival the combined brightness of billions of ordinary stars around it. These explosions scatter elements into space. Many atoms important to planets and life were produced by earlier generations of stars. The calcium in bones, the oxygen you breathe, the iron in blood, the carbon forming much of your body. Their cosmic histories stretch back into stars that existed before the sun. The phrase "we are made of stardust" is not simply poetic. It is fundamentally connected to astrophysics. Different elements form through different processes. Some are built inside stars. Some arise during stellar explosions. And some of the heaviest elements are associated with extraordinarily energetic events, such as neutron star mergers. The universe has been recycling material for billions of years. Stars form. Stars die. Their remains enrich space. New stars and planets form from material containing the products of previous generations. Our solar system is part of that cycle. When particularly massive stars collapse, they can leave behind some of the strangest objects in existence. A neutron star contains roughly the mass of a star, compressed into an object only around the size of a city. The density is almost impossible to imagine. A tiny amount of neutron star material would have an extraordinary mass under Earth-like conditions. The gravity at a neutron star's surface is immense. Its magnetic fields can also be unbelievably powerful. Some neutron stars rotate rapidly. If beams of radiation sweep across Earth as the star spins, astronomers detect regular pulses. These objects are called pulsars. When pulsars were first detected, their incredibly regular signals were so unusual that researchers briefly considered whether an artificial origin should be investigated. The explanation turned out to be natural. Rapidly rotating neutron stars. Some pulsars rotate hundreds of times per second. Imagine an object containing more mass than the sun, compressed into roughly the scale of a city, spinning faster than the blades of many machines. That is what nature can produce. Some neutron stars possess exceptionally powerful magnetic fields and are known as magnetars. Their magnetic fields are among the strongest known in the universe. Occasionally, they release tremendous bursts of high-energy radiation. And if a collapsing star is massive enough, even neutron pressure cannot halt the collapse. The result can be a black hole. A black hole is not a giant cosmic vacuum cleaner. Objects do not get mysteriously sucked toward it from enormous distances. Its gravity behaves like the gravity of any other object with equivalent mass when observed from sufficiently far away. If the sun could somehow be replaced instantaneously by a black hole of exactly the same mass, Earth would continue orbiting almost exactly as before. The obvious problem would be that sunlight would disappear. A black hole becomes unusual when you approach extremely close. Around it lies a boundary called the event horizon. Once something crosses this boundary, escaping would require traveling faster than light. According to our current understanding of physics, that cannot happen. so anything crossing the event horizon can no longer send information back to the outside universe. Black holes can form when very massive stars collapse. But stellar mass black holes are not the only kind. At the centers of most large galaxies lie supermassive black holes. These objects can contain millions or billions of times the mass of the Sun. Our Milky Way contains one called Sagittarius A star. It has a mass of roughly 4 million suns. Black holes themselves emit no ordinary light from inside the event horizon. But material falling toward them can become incredibly bright. Gas spiraling inward may form an accretion disk. Friction and other processes heat this material to enormous temperatures. Some actively feeding supermassive black holes power quasars. Quasars are among the brightest persistent objects in the universe. They can shine more intensely than the galaxies containing them. Black holes also distort time. General relativity tells us that clocks in stronger gravitational fields tick differently compared with clocks farther away. To a distant observer, processes near a black hole can therefore appear dramatically slowed. Black holes can collide with one another. When they do, they disturb spacetime itself. These disturbances travel outward as gravitational waves. In 2015, scientists announced the first direct detection of gravitational waves from merging black holes. The signal had traveled through space for more than 1 billion years before reaching detectors on Earth. For a brief moment during the merger, the power carried away in gravitational waves was extraordinary. And yet the disturbance reaching Earth changed distances by less than the width of a proton over kilometer-scale detectors. Humans had learned to measure a ripple in spacetime itself. Space is so large that kilometers become inconvenient. Astronomers often use the light year. A light year is not a measure of time. It is a measure of distance. It represents how far light travels through a vacuum in 1 year. Light travels at nearly 300,000 kilometers every second. In 1 second, it could circle Earth more than 7 times. Yet even moving at this enormous speed, light requires years to cross relatively nearby regions between stars. The nearest star system beyond our own is Alpha Centauri, just over 4 light-years away. That means when we observe it, we see light that left more than 4 years earlier. If hypothetical beings lived 50 light-years away and had an impossibly powerful telescope capable of seeing Earth's surface in detail, they would currently see Earth as it was 50 years ago. Looking through space is also looking backward in time. The Sun appears as it was 8 minutes ago. Neptune appears as it was several hours ago. Nearby stars appear years in the past. The Andromeda Galaxy appears as it was around 2.5 million years ago. Very distant galaxies appear as they existed billions of years ago. Astronomy gives us something close to a natural time machine. Not one that allows us to visit the past, but one that allows us to see it. Our solar system belongs to the Milky Way galaxy. The Milky Way contains hundreds of billions of stars, though exact counts are difficult. It is a barred spiral galaxy. From above, it would resemble an enormous rotating disk, with spiral structure extending outward from a central region. But we cannot simply fly outside it and take a photograph. Every image showing the entire Milky Way from an external viewpoint is therefore an artistic reconstruction or simulation based on observations. We live inside the disk. The Sun sits tens of thousands of light years from the galactic center. It takes our solar system roughly a couple 100 million years to complete one orbit around the Milky Way. The last time the Sun occupied roughly the same region of its galactic orbit, dinosaurs were part of Earth's ecosystems. Since its formation, the Sun has completed only a few dozen orbits around the galaxy. The Milky Way contains enormous clouds of gas and dust. Stellar nurseries. dead stars, neutron stars, black holes, planets, comets, and probably extraordinary numbers of worlds that we have never observed directly. Our galaxy is roughly 100,000 light-years across, depending on exactly which structures are included. Even if you could travel at the speed of light, crossing the main stellar disk would take around 100,000 years. And the Milky Way is only one galaxy. For much of human history, people did not know that other galaxies existed. Fuzzy patches visible through telescopes were sometimes called nebulae. In the 20th century, observations established that at least some of these objects were vast stellar systems located far beyond the Milky Way. One of our closest major galactic neighbors is Andromeda. The Andromeda Galaxy contains an enormous population of stars. It lies roughly 2.5 million light-years away. Despite that distance, under dark skies it can be visible to the unaided human eye. When you see Andromeda, photons are entering your eyes after traveling through intergalactic space for around 2.5 million years. Those photons began their journey before modern humans existed in our present form. The Milky Way and Andromeda are moving toward one another. In several billion years, the two galaxies are expected to interact and eventually merge. This sounds catastrophic, but galaxies are mostly empty space. Individual stars are so far apart that direct stellar collisions would be relatively unlikely. The shapes of both galaxies, however, would be transformed dramatically by gravity. Over time, they may form a much larger combined galaxy. Galaxies come in many forms: spirals, ellipticals, irregular galaxies, tiny dwarf galaxies, and enormous giants. They often gather into groups and clusters. Our Milky Way belongs to the local group. The local group itself is part of much larger cosmic structures. At enormous scales, galaxies form a web. When astronomers map galaxies across extremely large distances, matter is not distributed perfectly evenly. Instead, galaxies gather along enormous filaments and walls. Between them lie vast cosmic voids. This structure is known as the cosmic web. It resembles a network stretching across unimaginable distances. Gravity played a major role in shaping it. Slight variations in the density of the early universe grew over time. Regions containing slightly more matter attracted additional material. Stars and galaxies eventually formed within this evolving structure. Much of the mass influencing galaxies cannot be seen directly. Astronomers call it dark matter. Dark matter does not appear to interact with light in the ordinary way. It does not glow. It does not reflect enough light for us to observe directly. Yet its gravitational effects appear throughout the universe. Galaxies rotate in ways that suggest they contain much more mass than their visible stars and gas can account for. Gravitational lensing also reveals mass where there is not enough visible matter to explain the observed bending of light. According to modern cosmological models, ordinary matter, everything made from atoms, including stars, planets, people, and dust, represents only a minority of the universe's total contents. Dark matter appears to be far more abundant than ordinary matter. And yet we still do not know what dark matter actually is. Scientists have proposed various candidate particles. Experiments around the world continue searching. So far, no definitive dark matter particle has been confirmed. And dark matter is not even the largest mysterious component in our current model of the cosmos. That distinction belongs to dark energy. The universe is expanding. Distant galaxies, on average, are moving away from one another as the fabric of space expands. For many years, scientists expected gravity to gradually slow this expansion. But observations of distant supernovae in the late 20th century revealed something astonishing. Cosmic expansion appears to be accelerating. Something is causing the large-scale expansion of the universe to speed up. We call the unknown cause dark energy. The name is partly an admission of ignorance. We know something about its apparent effects. We do not know its fundamental nature. In the standard cosmological model, dark energy accounts for most of the universe's energy density. Dark matter makes up much of the remainder. Ordinary matter represents only a small portion. So everything familiar to us, every star you have ever seen, every planet, every ocean, every person, every atom in your body, belongs to the comparatively small ordinary component of the universe. Most of reality, according to our best current model, consists of things we still do not fully understand. If we look far enough into space, we look far enough into the past to approach the early universe. The universe has been expanding for roughly 13.8 billion years. Tracing that expansion backward leads to an early state that was much hotter and denser than the universe today. This is what the Big Bang model describes. The Big Bang was not simply an explosion occurring at one location inside empty space. It was an expansion of space itself. There is no known central point in ordinary three-dimensional space from which all galaxies are flying outward. From almost any galaxy, distant galaxies would appear to recede. A common analogy is dots drawn on the surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot. There is no special center located on the two-dimensional surface itself. The analogy is imperfect, but it helps. The early universe was extraordinarily hot. As it expanded, it cooled. Particles formed. Later, atomic nuclei formed. Eventually, electrons could combine with nuclei to produce neutral atoms. At that point, light could travel much more freely. Some of that ancient light still fills the universe today. We call it the cosmic microwave background. It is essentially a faint afterglow from the early universe. The light has been stretched by cosmic expansion into microwave wavelengths. When astronomers map the cosmic microwave background, they find tiny temperature variations. Those minute differences reflect early density fluctuations that eventually helped produce galaxies, stars, planets, and us. The largest structures in the modern universe grew from incredibly small variations in the ancient cosmos. There is a limit to how far we can see. Not necessarily because there is a wall, but because the universe has a finite age and light travels at a finite speed. We can only observe regions whose light has had enough time to reach us. This region is called the observable universe. Because space itself has expanded while ancient light traveled toward us, the present distance to the most distant regions we can observe is much larger than simply 13.8 billion light years. The observable universe has a present-day radius of roughly 46 billion light years. Its diameter is therefore around 93 billion light years. That number often surprises people. How can we see something currently farther away than the age of the universe measured in light years? Because the space between us and that matter expanded while the light was traveling. And the observable universe may be only a small portion of the entire universe. We do not currently know the total size. The universe beyond our observable horizon may extend vastly farther. It may even be spatially infinite. We simply do not know. For most of human history, we knew of planets only around the sun. Today, astronomers have confirmed thousands of planets orbiting other stars. We call them exoplanets. They reveal that our solar system is only one possible arrangement among many. Some planets orbit extremely close to their stars. Some take only a few days to complete a year. Some are enormous gas giants, much hotter than Jupiter. These are often called hot Jupiters. Some worlds appear to be larger than Earth, but smaller than Neptune. Our own solar system contains no planet in that size range, yet such worlds appear common elsewhere. Astronomers call many of them super-Earths or mini-Neptunes, depending on their properties. There are planets orbiting two stars. Planets orbiting stellar remnants. Planets in tightly packed systems, where several worlds orbit closer to their star than Mercury orbits the Sun. And there may be rogue planets traveling through interstellar space without orbiting any star at all. Finding exoplanets is difficult because planets are extremely faint compared with their stars. One common technique is the transit method. If a planet passes in front of its star from our perspective, the star's brightness dips slightly. By repeatedly measuring these dips, astronomers can infer information about the planet. Another technique measures the subtle gravitational tug a planet exerts on its star. The star and planet actually orbit a shared center of mass. Detecting the star's tiny motion can reveal the unseen planet. For some exoplanets, astronomers can study atmospheric composition. When starlight passes through a planet's atmosphere during a transit, different molecules absorb particular wavelengths. This can leave detectable fingerprints in the light. The long-term dream is to identify convincing evidence of life elsewhere. But this will be difficult. A single atmospheric chemical may have both biological and non-biological explanations. Scientists will need multiple lines of evidence before making extraordinary claims. We currently have only one confirmed example of life in the universe: Earth. That makes estimating the prevalence of life extremely difficult. Maybe simple life emerges readily wherever conditions are suitable. Maybe it is extraordinarily rare. Maybe microbial life is common while technological civilizations are rare. Or perhaps intelligence evolves frequently, but technological societies do not survive for long. We do not yet know. Our galaxy contains enormous numbers of stars. Many have planets. Some planets and moons likely contain environments where liquid water could exist. Chemistry involving organic molecules is also widespread. Complex organic compounds have been detected in meteorites, comets, and interstellar clouds. The ingredients associated with life are therefore not unique to Earth. But ingredients are not the same thing as living organisms. One famous question is called the Fermi paradox. If technologically advanced civilizations are common in such an old and enormous galaxy, why have we not seen obvious evidence of them? Many possible answers have been proposed. Perhaps intelligent civilizations are extremely rare. Perhaps they are too far apart. Perhaps technological eras are short. Perhaps we are looking for the wrong signals. Perhaps advanced societies communicate in ways we cannot recognize. Perhaps the galaxy is full of life, but mostly simple life. Or perhaps we are genuinely unusual. At present, every answer remains speculative. No confirmed extraterrestrial civilization has been detected. No verified alien signal has been received. And no confirmed extraterrestrial organism has been discovered. For all we currently know, the only beings in the universe contemplating the stars may be living here. Or there could be countless others doing exactly the same thing tonight. Some hypothetical and observed worlds are far stranger than anything in our solar system. There are exoplanets so close to their stars that their daysides may contain oceans of molten rock. Some planets are tidally locked, meaning one side permanently faces their star. One hemisphere experiences endless day, the other endless night. Between them could exist a narrow twilight region where conditions differ dramatically from either side. There are ultra-hot gas giants with temperatures high enough to vaporize metals. On some worlds, winds may transport vaporized material to cooler regions where it condenses. Some astronomical models and observations have inspired descriptions of exotic weather involving minerals or metals. There may be planets dominated by deep global oceans. Planets with atmospheres thousands of times thicker than Earth's. Frozen worlds hiding oceans beneath ice. And planets so dark that they reflect almost none of the starlight falling upon them. Nature appears under no obligation to make planets familiar. Between stars lies interstellar space. But interstellar space is not perfectly empty. It contains gas, dust, magnetic fields, cosmic rays, and clouds. Some clouds become nebulae visible through telescopes. Nebulae can form in different ways. Some are stellar nurseries where new stars are forming. Others are remnants of dead or dying stars. The Orion Nebula is one of the most famous star-forming regions visible from Earth. Inside it, gravity is gathering gas and dust into new stars and planetary systems. If you could watch such a region over millions of years, you would see an environment constantly transforming. New stars ignite. Radiation pushes gas outward. Disks around young stars evolve. Planets may begin assembling. The material forming a planet can include grains that existed before its star was born. Some microscopic grains found in meteorites are older than the solar system itself. They formed around ancient stars and survived long enough to become incorporated into the material from which our solar system formed. A tiny grain can therefore carry a history older than Earth. The universe is dynamic. Asteroids collide. Moons interact. Stars explode. Galaxies merge. Neutron stars crash together. But because astronomical distances are enormous, many of these processes unfold on timescales far beyond a human life. This can make the night sky seem permanent. It is not. Constellations slowly change as stars move through the galaxy. Given enough time, familiar patterns disappear. The Big Dipper will not retain its current shape forever. Neither will Orion. Our sky is a temporary arrangement. Even Polaris, the North Star, has not always been Earth's north celestial pole star. Earth's rotational axis slowly changes direction in a motion called precession. Over roughly 26,000 years, the direction of the celestial pole traces a circle through the sky. Different stars therefore become pole stars at different times. Ancient people lived under subtly different heavens. Future people will too. One of the strangest discoveries of modern physics is that time is not universal. According to Einstein's relativity, the rate at which time passes depends on motion and gravity. A clock moving very quickly relative to another clock can accumulate slightly less time. A clock deeper in a gravitational field can also tick differently. These effects are not merely theoretical. They are measured. Satellites used for navigation have clocks that experience relativity differently from clocks on Earth's surface. Systems such as GPS must account for these effects. Without relativistic corrections, positioning errors would accumulate. So whenever your phone determines your location using satellites, technology is quietly compensating for the fact that time itself behaves differently in different circumstances. At ordinary human speeds, these differences are tiny. Near the speed of light, they become dramatic. If a traveler could journey through space at a speed extremely close to light and later return to Earth, less time could pass for the traveler than for people who remain behind. This phenomenon is sometimes called time dilation. Travel into the future, in that limited relativistic sense, is therefore not just science fiction. Tiny versions of it happen continuously. According to relativity, the speed of light in a vacuum is a fundamental limit for matter and information. As an object with mass accelerates closer to light speed, increasing amounts of energy are required. Reaching light speed would require an infinite amount of energy under conventional physics. So spacecraft cannot simply accelerate until they move faster than light. This creates a tremendous problem for interstellar travel. Our galaxy is huge. Even traveling at 10% of light speed, which is far beyond the capability of current crewed spacecraft, reaching nearby stars would take decades. Crossing the galaxy would take around 1,000,000 years. Science fiction often solves this with warp drives, wormholes, or hyperspace. Physics contains mathematical ideas related to some exotic possibilities. But no practical faster-than-light transportation system is known to exist. For now, the stars remain very far away. Space is usually described as silent. This is largely correct. Sound is a mechanical vibration that needs a medium such as air, water, or solid material to propagate. Most of space is far too empty for ordinary sound waves to travel in the way they do through Earth's atmosphere. An explosion in space would therefore not produce a booming sound that nearby astronauts could hear directly through vacuum. But space contains other kinds of waves. Electromagnetic radiation travels perfectly well through a vacuum. Radio waves, visible light, X-rays, gamma rays, and gravitational waves can travel through spacetime itself. Scientists can convert measurements of these phenomena into audible frequencies for humans. So when you hear a sound of space released by a scientific organization, it is often data that has been translated or sonified into sound rather than something a human ear could literally hear floating in space. The actual vacuum would remain hauntingly quiet. The universe today is filled with stars. But star formation cannot continue forever. Gas available for creating new stars is gradually being consumed, expelled, or locked away. Far in the future, the rate of star formation will decline dramatically. Existing stars will continue living until their fuel runs out. Massive stars disappear first. Sun-like stars last longer. Red dwarfs can endure for trillions of years. Eventually, if our current understanding is broadly correct, even those extraordinarily long-lived stars will fade. The universe will become darker. White dwarfs will cool. Neutron stars will remain. Black holes will remain. Planetary systems may be disrupted over enormous timescales. This future era is sometimes called the degenerate era. The times involved are absurdly long compared with the present age of the universe. And even black holes may not last forever. In the 1970s, Stephen Hawking showed that quantum effects near black holes imply that black holes can slowly lose energy. This phenomenon is called Hawking radiation. For ordinary astrophysical black holes, the process is extraordinarily weak. They would take incomprehensibly long periods to evaporate. A black hole with the mass of the sun would survive vastly longer than the current age of the universe. Supermassive black holes would last even longer. Eventually, however, in a universe that continues expanding indefinitely, black holes could gradually evaporate. The final stages would occur only after timescales written with enormous numbers of zeros. Long after stars have stopped shining. Long after galaxies, as we know them, have faded. It is one possible glimpse into an almost unimaginably distant cosmic future. For now, however, we live during an unusually bright period in cosmic history. Stars fill galaxies. Planets orbit young and middle-aged suns. The universe is old enough to produce complex chemistry, but still young enough to contain abundant starlight. And from Earth, we can look upward and see part of it with our own eyes. Almost every point of light in the night sky is either an object inside our solar system or a star within the Milky Way. The vast majority of galaxies are too faint to see without assistance. Under truly dark skies, however, the Milky Way itself becomes visible as a pale band stretching overhead. That glow is produced by enormous numbers of distant stars blending together. For most of human history, before electric lighting, this sight was an ordinary part of nighttime. People built stories around the stars. They used them to navigate, to track seasons, to create calendars, to explain gods and heroes, to determine when crops should be planted. Long before humans understood nuclear fusion, galaxies, or general relativity, the sky was already a clock, a map, and a source of wonder. Many of the constellations we recognize today were named thousands of years ago. But different cultures created entirely different patterns using the same stars. The universe did not draw Orion. Humans did. We are remarkably good at connecting distant points and turning them into stories. Every photograph of space is, in some sense, a photograph of history. When a telescope photographs Jupiter, it is seeing Jupiter tens of minutes in the past, depending on where the planets are in their orbits. When it photographs a star 1,000 light-years away, it records light emitted around 1,000 years ago. A galaxy 10 billion light-years away appears as it existed when the universe was much younger. Some stars visible in telescopes may no longer exist in the form we see. Their light simply has not finished reaching us. Conversely, events happening in distant space right now may not be visible from Earth for thousands, millions, or billions of years. There is no universal cosmic now that we can observe everywhere. Information needs time to travel. The universe therefore reveals itself layer by layer, with distance and history intertwined. If you wanted to write Earth's complete cosmic address, it might look something like this. You are on Earth. Earth orbits the Sun. The Sun belongs to the solar system. The solar system sits within the Orion Spur, sometimes called the Orion Arm or local spur, a smaller structure associated with the Milky Way's spiral pattern. The Milky Way belongs to the local group. The local group contains dozens of galaxies. It lies within a much larger region of cosmic structure, often associated with the Laniakea supercluster. And all of this exists within the observable universe. There is something strangely comforting about that address. Your room may feel very small. Your city may feel large. Earth feels enormous when crossing it by plane. But from the scale of the solar system, Earth becomes a point. From the scale of the Milky Way, the entire solar system disappears into insignificance. And from the scale of the observable universe, even the Milky Way is one galaxy among extraordinary numbers of others. Yet this tiny world contains oceans, forests, music, languages, libraries, memories, and creatures capable of discovering the age of stars they could never visit. In 1990, the Voyager 1 spacecraft turned its camera back toward Earth from billions of kilometers away. Earth appeared as a tiny point of light, less than a pixel in the famous image, a pale blue dot suspended in sunlight. Every human civilization known to history existed on that point. Every war, every journey, every person who ever looked toward the night sky and wondered what was out there. From far enough away, everything that feels enormous becomes tiny. Our planet is not the center of the solar system. Our sun is not the center of the galaxy. Our galaxy is not the center of the universe. And as far as modern cosmology can determine, the universe may not have a center in the ordinary sense at all. Humanity spent centuries gradually removing itself from imagined positions of cosmic importance. And somehow, the universe became more interesting each time. There are stars whose light has traveled toward Earth longer than our species has existed. There are planets no human will ever see directly. There are galaxies so distant that their light began traveling before the sun was born. There are black holes that will outlive almost everything currently shining. There are mysteries occupying most of the universe's contents that we have named dark matter and dark energy largely because we still do not know what they truly are. And here, on one rocky planet orbiting one ordinary star, matter has somehow arranged itself into something capable of asking questions about all of it. Atoms forged in ancient stars became planets. Some of those atoms became oceans. Some became living cells. And some eventually became a brain capable of thinking about the stars that created them. Perhaps somewhere else in the universe, on another world beneath another night sky, something is doing the same. We do not know. And maybe that uncertainty is one of the best things about space. There is still so much left to discover. For tonight, though, our journey ends back where it began. On Earth, beneath a thin atmosphere, orbiting a star, inside a galaxy, surrounded by a universe larger, older, and stranger than anything our ancestors could have imagined. And whether you stayed awake for every fact or drifted off somewhere near Saturn, thank you for visiting the subconscious library. Good night.